Okay, so today we're going to talk about UV visible spectroscopy and the Jablonski diagram. We'll talk about fluorescence and phosphorescence and essentially all the things that are happening in the visible region of the spectrum. We'll also explain a little bit more about color. Y'all had the color lab, and so I'll show you a spreadsheet tool that I made that you guys can have. I don't think I uploaded it with that lab, but if y'all want it, it's a fun little tool to play with, and so I'll walk you through those things. So this week's lab is the iodine lab, which is the really row vibronic lab, but you don't resolve the rotational lines, and so it's the vibronic lab. So what is that word vibronic? Think about the two pieces. There's vibe, which stands for vibration, and ronic is a piece of like electronic. And so these terms where you see resolved vibrational transitions on top of an electronic spectrum is row vibronic or vibronic spectroscopy. So we're actually going to put iodine in the cell. It's a 10 centimeter cell. We run visible light through it, and we get, iodine's purple. It's kind of a purplish gas. So it absorbs in the visible region. Now it takes about 35 to 40 minutes to collect this spectrum, and you just kind of stand there and look at the spectrometer. So you really can't tell that anything's going on, but it's going very slowly at the highest resolution that we can get out of our spectrometer. And we see the vibrational transitions on top of the electronic transition. So this is what's going on. This potential energy surface here is the ground electronic state and the excited electronic state. So it's electronic spectroscopy. And then on top of that, you have different vibrational levels. And it's a diatomic, so you can draw the potential energy surface. This same thing happens for polyatomics, but once you get to so many degrees of freedom in terms of the bonds and bond angles and bond lengths, you can't really plot the potential energy surface. But for a diatomic, it's easy. You just have one bond length and the energy related to that bond length. So that's what we have here. We have the ground electronic state and the excited electronic state. And we have the transitions and the ground electronic state. Notice how they're shifted a little bit compared to the excited electronic state. You see they have different minima. That tells you they have different bond lengths. So look at the excited electronic state. You see it's shifted to the right. That means it has a little bit longer bond length. Now that's going to happen if you take an electron from a bonding orbital and promote it to an anti-bonding orbital or a non-bonding orbital. You've weakened the bond in the molecule, and the internuclear distance has increased. So you have a weaker bond, so you have a longer bond length. Another thing that we notice is look at the ground vibrational wave function. It's a Gaussian function. It's big in the middle and small at the edges. And that also, if you were to square that wave function, is the location of that molecule in terms of its bond length. It spends most of its time at that equilibrium bond length, a little bit time stretched from that and a little bit of time compressed, but most of the time it's right there at its equilibrium bond length. Light comes in, hits that molecule, and this is the most probable position of that molecule, and right above that is the 14th vibrational level in the excited electronic state. And so these wave functions, you see this wave function up here, that's the vibrational wave function, and it's got a big bump right there close to this turning point. It's also got a big bump over here close to that turning point, but if we were to take this wave function and multiply by that wave function, the pieces that are non-zero, this piece here and that piece there, are going to contribute to the integral. Remember, the transition probability is based upon the wave functions times each other. And so if one wave function is 0, where the other wave function is the maximum, there's really not any overlap, because you have 0 times a big number. But if you have big number times big number, then you've got a large integral, a large probability of excitation, a large intensity to that peak. So we can actually see the intensities of the peaks vary based upon vibrational level. And you're going to see that in your spectrum this week. So you're going to see the transitions grow in and grow out based upon how far away they are from that optimum vibrational overlap. And this overlap in the visible spectrum was called the Franck-Condon factor. The scientists Franck and Condon solved this problem, did the math, and so they got it named after them. But it's no different than the transition dipole moment integral. But in UV-Vis spectroscopy, it's called the Franck-Condon factor. And so that's what we have. This Franck-Condon factor calculates the overlaps of the wave functions and light. It's that light, it's the transition dipole moment integral. And then this also uses that Born-Oppenheimer approximation because the nuclei move so slowly compared to the electrons. And so that Born-Oppenheimer approximation says that the motion of the nuclei are separate or separable from the motions of the electrons. And so we have this, it's called a vertical transition. The nuclei are moving back and forth on this plot. So you can see the internuclear distance. When the nuclei stretch apart, you're moving to the right in this plot. When they squeeze together, you're moving to the left. But when light comes in, it's so fast, it's a snapshot. Wherever that nucleus is, wherever those two nuclei are, the electron cloud is fixed and light comes in and causes it a vertical line. What if it wasn't vertical? If you could change the nuclei and the electrons together, you could do this. See this diagonal? You could go minimum to minimum. But the Born-Oppenheimer approximation says that can't happen because the nuclei would have to stretch while the electron's moving, and it's just the electrons are too fast and light's too fast. The nuclei are slow. There's no way they could move out to that other minimum that fast. Light comes in, electrons move, and the nuclei are saying, what happened? So this path is not allowed. This diagonal does not happen. They're vertical transitions. Wherever the nuclei are, boom, the electrons jump. Now the nuclei find themselves on an excited electronic state. So these nuclei are all happy. They're at the equilibrium bond length. Light comes in, causes excitation, and now the nuclei are up here, kind of on this repulsive side of the potential. And so then they are excited vibrationally and start oscillating around this spot. So now they have a new favored nuclear position. They're in the 14th vibrational excited state. And so they can hop down eventually and get to the ground state in the excited electronic state. So you got to listen carefully. When I talk about excited states, raise your hand if you're confused and say, are we talking about the vibrational excitation or the electronic excitation? Because we have two things going on. Just like we did for the rotation vibration, we had two things going on there. Here we have two things going on. We have two electronic states and we have a bunch of vibrational states. And we can be excited in both or neither. So that's the lay of the land, and that's what this lab is about. And so let's keep going. What causes these different electronic states? Well, the different molecular orbital diagrams. And we're going to dive into molecular orbital diagrams next. But I like to cover the spectroscopy first because you're about to do a lab on this. If we held this back behind the MO theory, you would do the lab first and then learn about it. And that's never fun. And so that's why we're kind of out of sync here. We're covering the electronic potential energy diagrams before we've done molecular orbital theory, but I want to get you prepped for the lab in your thinking and what's going on. And then we'll actually explore that panel on the left. That panel on the left is the molecular orbital diagram, and we'll learn how to make those next. But however you put the electrons in this molecular orbital diagram, I mean, you have some sigma bonds and some sigma antibonds. You have some pi bonds and pi antibonds. However you put these electrons in this molecular orbital diagram will give you a different potential energy curve, and I've color-coded them. So this green one here is the ground state molecular orbital diagram shown over here, where you have two unpaired electrons, and this is all for oxygen. You have two unpaired electrons spin up. It's a triplet for the ground state for oxygen, and that's what you have for the ground electronic state. That's the most stable electron cloud for that molecule. It's not much different in energy, but it is a little higher if you pair those electrons and put them in the same orbital. So if we, instead of having two spin unpaired electrons in different orbitals, if we paired them up and put them in the same orbital, that'd be a little bit higher energy. And that's this curve right there. Everybody see that? Okay. What if we put them paired up, but put them in the sigma antibonding orbital? Then that's this blue one down here. What if we left them spin unpaired, and we just put one instead of the pi star, we put it in the sigma star? That's this one right here. And I'm actually not sure where the red one is. I don't know the electron configuration for this red one. But also notice the different nomenclature. We have the X state. So this is the important one here. The X state is the ground state. And so that applies even though this is oxygen on the screen, because this is the only one I could find in the textbooks. Iodine looks very similar to this. And the X state is the ground state for the electronic potential energy surface. And we're going, in iodine, we're going from the X state to the B state. So we're going from here straight up to there, and that's in the visible region. So for iodine, we're going from X to B. And we'll see that in a second. But I just wanted to show you here, the potential energy surface for the internuclear distance is based upon the molecular orbital diagram, and we're going to come up with those in the next set of notes. Does anybody need clarification on this? Please raise your hand.
What's
Yes.
that? Add an X to that? Q?
I'm looking at that. I think that means triplet. So I think that's X triplet. The A1 is singlet because they're paired up. The B1 is singlet because they're paired up. And then the yellow one is a triplet again.
Okay.
Yeah. Now these Greek letters, the sigma, G minus, and delta G, and so on, initially when they did the point groups, they used Greek letters for these. And the first point groups they came up with were the linear molecules. So D infinity H and C infinity V. First two molecules studied were the linear molecules. And so the Millikan notation, A1, B1, you know, those kinds of things, they used Greek characters. So this sigma G minus or whatever, that's essentially A1G. And so again, the source that I got these, this is the Atkins source I got these from, they used the Greek character from the character table. But I've converted in your character tables, I've converted these all to A1s and B1s. And so those are the Millikan notations for these various potential energy surfaces. All right. Good question. So let's look now. We've excited the molecule, and what happens to it? Those excited states are going to do something. We call those the fates of the excited states. They can move from one potential energy surface to another with the same multiplicity, and they can do that very easily and very quickly. They can, and that's called internal conversion. They can do intersystem crossing, which is movement from one potential energy surface to another with a different multiplicity. So in moving from one potential energy surface to another, you can have a spin flip with the electrons, and you can either unpair the electrons or pair them up. And that would be intersystem crossing. If you have a change in multiplicity, the number of unpaired electrons, then you've got an intersystem crossing. So you've got to learn the difference between those two words. So those are your good vocabulary words. You got to make sure you internalize that. You could have dissociation. You could hit a vibrational energy level. Actually, you could hit a point on the excited potential energy surface that was above all of the vibrations and then just break the molecule apart. So if you hit iodine with UV light, it's going to go to the potential energy surface that would result in two atoms. So you could dissociate the molecule with light. And so that would be photolysis or photolytic dissociation. So you can take the molecule, hit it with a photon of light, and cause the molecule to break apart. And that's really what's happening with environmental degradation, with light, coming in from the sun in the UV region. It's breaking materials down. It bleaches, dyes. If you've got an old shirt, you wonder why the color isn't the way it always was in the past. You get photo bleaching. Light's causing these molecules to be more reactive, and right there's oxygen in the atmosphere, and it can take advantage of these excited molecules and start to break them down. And then predissociation, we'll show a picture of that. It's a little hard to understand text-wise. It's better with the picture. But it's internal conversion from a bound potential energy surface, in other words, one that has a dip in it and it comes back up, to an unbound, one that doesn't come back up. So you can hit sort of a ramp that leads to an exit where the atoms just come apart. So then we have two different types of transitions that emit light. We have fluorescence and phosphorescence. So if we could have, if we had intersystem crossing and we went to a triplet state in the excited state, and it couldn't get back down to the singlet state without flipping a spin, we could have triplet to singlet emission, which is phosphorescence, and then singlet to singlet or triplet to triplet would be fluorescence. So if there's no change in multiplicity, that's fluorescence. If there is a change in multiplicity, that's phosphorescence. Since changing the multiplicity and emitting light is forbidden, it takes a long time for that to happen. So we don't know exactly what causes that jump, but statistically, if you wait long enough, it'll happen. So the forbidden part isn't that it's forbidden forever, it's just not a quick transition. So phosphorescence takes a lot longer because it has a longer lifetime in the excited state. And fluorescence can take place very quickly. So fluorescence can take place like in 10 to the minus 15 seconds or 10 to the minus 12 seconds, very fast. It's not instantaneous, but it's pretty fast. But phosphorescence can go on for seconds, and that's what the glow-in-the-dark stuff is. For Halloween, the glow-in-the-dark paint is taking advantage of phosphorescence. So let's talk about these fates of excited states instead of just textbook definitions. Let's look at the pictures, because I'm very visual myself. So we have absorption, and then we have non-radiative relaxation, and then you have radiative emission. So what's going on with this non-radiative relaxation? We say it's non-radiative because it's not in the visible region. It still is emitting infrared light, but we just classify that as non-radiative because in these electronic spectroscopies, we're using visible spectrometers, UV visible spectrometers, and so we don't see that light, so it's non-radiative. But if you were to try to be technical and say, well, technically it's infrared emission, it's non-radiative as defined by the visible spectrometer. There are IR photons coming out of that. Okay. Now we have intersystem crossing, which is a possibility. So here we have absorption. Let me just draw the path here. We start in the ground state. The Franck-Condon factor, basically if you map this wave function onto the side of this one, you'll see it's very likely to hit up here. That's straight above this maximum. So the absorption puts this molecule here and up on the wall of this excited electronic state, and it's a singlet. And it emits light, or photons of infrared light, until it gets down to this vibrational level, which corresponds to the same vibrational energy as this triplet state. And so that's the most probable time that an electron will flip. So using my fingers as electrons, we have a singlet ground state, so they're spin paired. And then light hits it and one gets excited. So we take one electron up, they're still spin paired. But this is not the ground state electron configuration. So the whole molecule is excited and it's in that upper excited state. And then the molecule's bouncing around, and as it's bouncing around, the electron cloud gets more stable. So it's going down in vibrational level, and then eventually that electron flips. And now it's on the triplet excited state, and it can actually get lower in energy, you see. because again, the higher the multiplicity, the sort of the lower the energy. And so it flips, and now it's on the triplet excited state, and it can go lower in energy. If it was staying in the singlet, it could get down to say right about there. But if it flips, it could go a little bit lower. And so this would be the lowest it could go for the singlet. This is the lowest it could go for the triplet. So it flips where those vibrational levels are very close together. So this is called the intersystem crossing point, and now it's on the blue curve, and it ends up right here. That's going to have a ground state wave function. That's a Gaussian. And so the most probable place for that molecule to be in excited state is right here, and that's right above this vibrational level. And so we might have V double prime equals 0, and this might be 14. V prime equals 14. And then it does all its business and ends up here at V prime equals 0. And that's above V double prime equals 0, 1, 2, 2. So what we would see in the spectrum is we would see this peak okay, so let's look at this too. This is an absolutely enormous arrow. You see that? So that's going to be a short wavelength. This is a puny little arrow. And so that's going to be a long wavelength. So we would have an absorption spectrum with a maximum over here at the short end of the spectrum, and then we would have a phosphorescence spectrum with a maximum way over here in the long wavelength section. One's an absorption spectrum, one's an emission spectrum. Clarification on this. We'll see a spectrum plotted in a future set of notes, so we'll keep going. Here we've kind of plotted that spectrum on the side. So this would be the ground vibrational state and the ground electronic state. And it's hitting all of these vibrational energy levels in the excited electronic state. And you get a little peak or a bump in the spectrum that lines up with all of these vibrational levels. You see that? Because that's where the transition probability is large. So we do that transition dipole moment integral. We have the ground state, the excited state, times light, integrate over all space. That's your intensity. Wherever those wave functions line up, then you get a bump, you get a peak. Okay? And so you could assign this, and this is what you'll do in your lab. Like this peak right here will be V double prime equals 0 to V prime equals, and so this is 0 here, 1, 2. So 0, 1, 2. So that's going to be V prime equals 2. So every one of those little bumps can be assigned to a particular vibrational transition. Notice because of anharmonicity, there's a vocabulary word for you, the anharmonic nature of that upper potential, those vibrational levels get closer together, don't they? And so they get a little bit more difficult to assign as they get closer together. You see these little bumps are close, and then you see it get kind of noisy, and then you just see this, no more bumps. You still have absorption, still have this region of absorption, but there are no bumps anymore. And you say, wow, what happened to my vibrational transitions? This, where you see distinct vibrational levels and where they disappear, that's the dissociation limit. So if I take that ground state molecule and excite it to right here, it's just like if you put a ball on this hill Is that ball going to get trapped in the well? No. If you put a ball right there, it's going to go down with enough kinetic energy that it comes back up and out. So you can think about this potential energy curve just like a ball. If you put a ball at one of those vibrational levels, it's going to go to the other side and just oscillate. Now, they won't have any friction, okay? So it'll just oscillate, and the turning points will be, you know, like if I put it in this 2 level, the ball right there would just oscillate down and back up and turn around right there and go down and back up. And so it oscillates back and forth between those 2 turning points. But if I get that ball up above the dissociation limit, down it goes and then out, and the molecule just dissociates. So I really like these potential energy surfaces because they make sense to me, even from a classical sense. If I put a ball on there and it's going to roll out of the well, then I'm at the dissociation limit. If I put it at a particular vibrational level and I don't have any friction, it's just going to go back and forth forever. Now, sometimes we've noticed that the vibrational structure will disappear for a little bit and then come back. And so there's a region here on this one. You get the nice vibrational transition. You get another nice vibrational transition. And then you miss a few. And then they come back. And you're like, well, what's going on right there? Well, as we've looked into it, we've realized that's where it intersects another potential energy surface. And so I excite a molecule here, that ball rolls downhill, and then it finds another path out and it disappears, like the molecule gets broken apart. And so that's called predissociation. I haven't given it enough energy to dissociate from that first potential energy surface, but it finds another path. And so this is how we learn about the excited states of molecules. It's really complicated in trying to get all of these energy level surfaces mapped out for a molecule, especially something more complicated than a diatomic. But that's what we use Gaussian for. A lot of times we'll use Gaussian to try to map out the excited states. But even then, some of those calculations take months to do. You can talk to Dr. Arnie about some of his triplet, singlet excited state calculations. And you know, it's pretty complicated and very difficult to get Gaussian to follow those energy levels because you know, you've heard of herding cats. It's even more difficult to herd electrons. Okay, so that's essentially what you're trying to do to map out those excited state potential energy surfaces. But anyway, this is what dissociation versus predissociation. Dissociation is you've given it enough energy to dissociate without any other potential energy surfaces. And predissociation, this is below this limit. It's below that limit, but it finds another path out and it dissociates. Now let's look at the spectrum. I kind of talked about this earlier about assigning the V double prime equals 0 to V prime equals 2. Oh, this is the emission and absorption spectra. Here's the potential energy surfaces over here on the right, and what you actually get in the lab, the experimental data is on the left. A lot of times you'll do just an absorption experiment. That's what we're doing, and we're seeing these various transitions. And so we can label these like 0, 0, or I like to be more explicit and say that I'll come up here and label this one. That's the V double prime equals 0 to V prime equals 0. So that's the 0 to 0 transition. It's not very likely because look over here, this probability of the molecule being there and going up here to there is pretty low. You see, those wave functions have a low value there. So when you take those small numbers and multiply by each other and then integrate, it's a pretty small result. So it's not very probable, but it is possible. And sometimes the potential energy surfaces are so far away, you just don't have the 0, 0 transition. If the bond lengths are drastically different, then there's really no overlap. But in this case, there's just a little bit of overlap, and you can see that 0 to 0 transition. If we take the difference between those energy levels, so we take this energy level and subtract that, we get the difference in energy, convert that to wavelength, and that's what you have right here. This is the wavelength of that energy difference. Now notice this is wavelength increasing in this direction. So this is long and short wavelengths. So notice on the absorption, if I want to hit any of the other vibrational levels, the arrow has to get longer. And long arrows are short wavelengths. So the absorption spectrum is to the short wavelength side of the 0-0 transition. If you don't picture these potential energy surfaces in your mind, it's very hard to keep this straight. But the longest wavelength absorption is the 0-0 because that's the shortest arrow. So this is the shortest arrow, this red one, right here. Every other arrow on the absorption side is going to be longer, and so that's going to be a shorter wavelength. Longer arrows give shorter wavelengths. So let's take the most probable one, this blue one. Goes way up here and hits this vibrational level here. See, that's a pretty long arrow, so that's a pretty short wavelength. It doesn't actually match this spectrum very well. This spectrum says the 0 to 0 is here, the 0 to 1 would be there, the 0 to 2 would be there. So this spectrum tells us that the 0 to 2 should be the strongest peak, and so it'd be, this is the 0, 0, 0, 1, 0, 2, so it should be this one is the strongest peak. But the way I've drawn this diagram over here, it really shows like 3, 4, 5, 6 would be the strongest. Okay, so those don't exactly line up with the spectrum, but they're pretty close. Okay. So is there any question about the absorption side of things before we do emission? Understanding this slide will really help you with the lab. Because if you can't keep straight what's going on in your mind, you just have V double prime and V prime, and there's 100 of them. And it's so confusing. But if you have a mental picture of what you're looking at in the experiment, then it makes sense. And we're just doing absorption in this lab. So it's a little easier than what's on this picture. Okay, so we have this molecule. It's excited by light. And then it spits out some infrared as it relaxes down. And it comes down here to the ground vibrational state and the ground electronic state, and then starts to emit. Now, once again, the most probable location for that excited state molecule is right here, and so it's going to overlap with, say, this one here. The spectrum says it overlaps with the 0, 1, 2, 3, so it's overlapping with the third state here. But again, it's not exactly matching this picture in this potential energy surface, but the spectrum would tell us that the minimum is directly over the turning point for the third vibrational state. Now, why do the fluorescence peaks, why are the fluorescence peaks at long wavelength? They're red shifted from the absorption peaks. Yeah, the 0 to 0 is the longest emission arrow. So that's the longest emission arrow, so that's the shortest wavelength in the emission. Every other arrow is shorter than that. You see that? We start from, so all the emission peaks start from this level. This is the starting point for emission. And the final points are these vibrational levels. And you see all of those vibrational levels are going to be shorter arrows. Shorter arrows give longer wavelengths. Okay, almost done. And so then this gets really complicated. So Jablonski just kind of punted and said, okay, for all of these vibrational levels, I'm just going to draw a box for the ground electronic state and just put a bunch of lines in it. Okay, so this right here represents that ground electronic state, and these are the vibrational lines, and they're not accurately drawn, they're just drawn in, you know. And then this one is the singlet excited state, and so I'm just going to get the minimum difference correct So that minimum difference occurs at an energy difference that's 315 nanometers. And then this would be the triplet. And I'm going to call the singlet a capital S with a lowercase 0 for the ground state. The first excited singlet would be S1. And then the triplet would be T1. And that's the green. And so follow along with this. We have absorption. And then we have non-radiative relaxation. Okay. We could do an intersystem crossing and go to the green, and we could have non-radiative relaxation. And we could have phosphorescence come from that level. Or we could cut straight across to S0 and do non-radiative relaxation all the way to the bottom. So we don't have to emit light. We could vibrate our way all the way down to the ground state if these potential energy surfaces overlap. If they don't overlap, then we have visible fluorescence and phosphorescence. And so we would see a colored substance, in that particular spectrum. So that's the Jablonski diagram there on the left. And that's what's going on. When we draw the little wiggles, we mean non-radiative relaxation. When we draw straight arrows, we mean light, either absorbed or emitted. And then the chromophore stuff's pretty straightforward. I'll talk about the colors next time. So have a good day.